Good morning everyone, myself Muskan from B.sc Chemistry Honours 2nd year. Today I am going to make an audio recording on chapter distribution law of physical chemistry. Nernst distribution law definition. Nernst distribution law studies the distribution of a solute between two immiscible solvents in contact with each other. When a solute soluble in two immiscible solvents is added to a mixture of these solvents, the concentration of solute in both the solvent layer is different. In other words, the solute distributes itself in both the solvents. For example, when a dilute solution of iodine in water shaken with carbon tetrachloride, the iodine distributes between two immiscible solvents. Iodine is about 86 times more soluble in carbon tetrachloride than in water. Due to higher solubility, most of the iodine passes into CCl4 layer. In simple words, iodine is distributed between two immiscible solvents, water and carbon tetrachloride. Nernst in 1891 showed that when a solute is added to a mixture of two immiscible liquids in both of which it dissolves, then it distributes itself between both the liquids in such a way that the ratio of concentration of solute in both the liquids remain constant at constant temperature. However, this ratio is constant only when the solute has same molecular state in both the solvents. That is, the solute neither undergoes association nor dissociation in both these solvents. The generalization put forward by Nernst is called Nernst distribution law and is stated as: a solute distributes itself between two non-immiscible solvents in contact with each other in such a way that at equilibrium the ratio of the concentration of the solute in two layers is constant at a given temperature, provided the molecular state of the solute is same in both the solvents. If a solute X distributes itself between solvents A and B, the distribution law is written as concentration of X in solvent A upon concentration of X in solvent B is equals to C1 by C2 is equals to K. The constant K is termed as the partition coefficient or distribution coefficient. Factors affecting partition coefficient: number 1, nature of solute; number 2, nature of liquid pair; number 3, temperature. Number 1, nature of solute. For a particular liquid pair, different solute have different solubility, hence the value of partition coefficient will be different for different solute at a given temperature. It is clearly seen from the data. Number 2, nature of liquid pair. A given solute has different partition coefficient in different liquid pair as shown in table. Liquid pair, water and ether. Solute, succinic acid. Partition coefficient, Kelvin at 293 Kelvin 5.423. Liquid pair, water and benzene. Solute, succinic acid. Partition coefficient 0.096. Number 3, temperature. The solubility of a solute in a particular solvent changes with temperature. As the temperature is changed, the solubility of a solute in a given liquid pair also changes. Therefore, the partition coefficient also changes with temperature. The change in value of partition coefficient K for 1 degree rise in temperature is known as temperature coefficient. However, the value of temperature coefficient is generally small. System: acetic acid in water and ether. Temperature coefficient 0.0064. Table below shows value temperature coefficient for some system. Succinic acid in water and ether. Temperature coefficient 0.55. Experimental verification of distribution law. Solution of iodine in carbon tetrachloride of different concentration are shaken with water taken in different bottles. These are allowed to stand undisturbed till the two layers separate out. A known volume of CCl4 layer and aqueous layer is pipetted out and titrated against standard sodium thiosulfate solution, and the concentration of iodine is determined. The following result from the distribution of iodine between CCl4 and water shows the consistency of ratio of concentration in each layer. These results shows that the ratio C1 by C2 is almost constant, hence the distribution law is valid in this case. Condition for validity of distribution law. Limitation of Nernst distribution law. The distribution law in its simple form, that is K is equals to C1 by C2, does not hold under all conditions. Some limitations and the conditions under which the law is applicable are as follows. Number 1, temperature should be kept constant. The solubility of a solute in both the liquid changes with change in temperature. This may result in change in concentration in both the solvent. Moreover, change in temperature may affect the mutual solubility of the two solvents. Therefore, with change in temperature, a different value of partition coefficient is obtained at every temperature. Hence, the temperature should be kept constant throughout the determination of partition coefficient. Number 2. The two solvent should be immiscible or sparingly soluble. Number 3. The mutual solubility of two solvents should be affected by addition of solute. Number 4. The solution should be dilute. Distribution law holds good for dilution solution. As the concentration of solute increases, the deviation from distribution law between more and more pronounced. Number 5. The molecular state of solute should be same in both the solvents. This law is not valid under following two conditions. Number 1. When the solute undergo association, the law in simple form is not applicable. When the solute under association in any of the solvent, for example, distribution law does not hold for phenol distributed between benzene and water, because phenol undergo association in benzene to form dimers. Number 2. When the solute undergo dissociation, the distribution law is also not valid for solute which undergo dissociation in any of the solvent. For example, electrolyte like HCl undergo dissociation in water, and hence its solution in a mixture of water and an organic solvent, benzene, CCl4, CS2, etc., does not obey distribution law in this simple form. Modification of distribution law with change in molecular state of solute. Nernst showed that the ratio C1 by C2 is constant, that is K is equals to C1 by C2, is applicable only when the solute has the same molecular condition in both the liquids. That means the solute does not undergo association or dissociation in any of the liquids. However, if any of such changes take place in one or both the liquids, then the distribution law gets modified. Let us consider cases in which a solute may associate or dissociate or enter into chemical combination with one of the solvent. Case 1. When solute undergo association in one of the solvents. Suppose a solute X remains in the normal molecular state in phase 1, whereas in phase 2, n molecules of X undergo association to form complex molecules Xn, as shown. Solute X undergo association in solvent 2. Here two equilibria exist simultaneously, that is number 1 X equilibrium X, number 2 Nx to Xn. Suppose that the total concentration of solute X in phase 1 is equals to C1. The total concentration of solute X in phase 2 is equals to C2. If alpha is the degree of association of solute in phase 2, then the concentration of associated molecule in phase 2, that is Xn, is equals to 1 by n C2 alpha. That is, the concentration of normal molecule in phase is equals to 1 minus alpha C2. Applying distribution law to the distribution of X in the two solvents, we can write concentration of X in phase 1 upon concentration of normal molecule of X in phase 2 is equals to K. That is C1 upon 1 minus alpha into C2 is equals to K. Applying law of chemical equilibrium to the polymerization process Nx to Xn, we can write the equilibrium constant K equilibrium as concentration of associated molecule in phase 2 upon concentration of normal molecule in phase 2 n whole power n is equals to K equilibrium. 1 upon n C2 alpha upon 1 minus alpha C2 whole power n is equals to K equilibrium. Taking nth root on both sides, n under root C2 alpha 1 minus alpha C2 upon 1 minus alpha C2 is equals to constant. Dividing equation 1 by 2, we get C1 upon n into under root C2 dot alpha K upon K equilibrium is equals to constant. However, the molecule in phase 2 are completely associated, that is alpha is equals to 1, then equation 3 becomes C1 upon n under root C2 is equals to constant. This relation is used in determining the value of n, the extent of association of molecule. The values of C1 and C2 are determined experimentally and substituted in equation 4. putting n is equals to 1 to 3 up to dot etc. The value for which a nearly constant value of k is obtained is equal to n. Equation 4 has been verified by studying the distribution of benzoic acid between water and benzene. Benzoic acid exists almost entirely as dimers C6H5COOH whole square in benzene, but in normal state in water. Evidentially, the ratio C1 by C2 is not constant, hence benzoic does not exist as single molecule in benzene. A fairly constant value of C upon under root C2 shows that the benzoic acid exists as dimer in benzene. The method to calculate N has been explained in section this. Case 2. When the solute undergo dissociation in one of the solvent. Let a solute X dissolve in phase 1 in its normal state and undergo dissociation in solvent 2. The two equilibria existing simultaneously are number 1 X to X, number 2 X to A plus B phase 2. Total concentration of X in phase 1 is equals to C1. Total concentration of X in phase 2 is equals to C2. The degree of dissociation of solute in phase 2 is equals to alpha. That is, the concentration of undissociated molecule in phase 2 is equals to 1 minus alpha into C2. Applying distribution law, the ratio of concentration of solute in equilibrium as given C1 upon C2 into 1 minus alpha is equals to K. On the other hand, when the solute is dissociated in phase 1 having degree of dissociation alpha and remains undissociated in phase 2, then the partition coefficient is given by C1 into dot 1 minus alpha upon C2 is equals to K. Case 3. When the solute is dissociated in both the solvents, it is evident from that the concentration of the solute in layer 1 is C1 into 1 minus alpha and layer 2 is C2 into 1 minus alpha, where alpha is the degree of dissociation of solute. The partition coefficient is given by C2 into 1 minus alpha upon C1 into 1 minus alpha is equals to K. Case 4. When the solute enter into chemical combination with one of the solvent. Suppose the solute X remains in normal molecular state in solvent 1, but one molecule of X combined with N molecule to solvent in phase 2 to form X dot Ns molecules. Following equilibria exist simultaneously. Number 1 X to X phase 1, number 2 X plus Ns to X dot Ns phase 2. Let us concentrate of solute X. Concentration of solute X in normal state in phase 1 is equals to C1. The concentration of X in normal state in phase 2 is equals to C2. Concentration of solvent molecule in phase 2 is equals to Cs. Concentration of complex molecule in phase 2 is equals to Cc. Applying distribution law of equilibrium 1, we get C1 by C2 is equals to K. Applying law of chemical equilibrium to equilibrium 2, we get Cc upon C2 into Cs whole power n is equals to K1. In dilute solution, the concentration of solute in phase 2 is in excess, therefore its concentration Cs remains practically constant. Thus equation 2 takes the form Cc by C2 is equals to K1 into Cs, n is equals to K2 constant. Adding 1 to both sides, 1 plus Cc by C2 is equals to 1 plus K2 is equals to C2 plus Cc upon C2 is equals to 1 plus K2. Dividing equation 1 by equation 3, we get C1 upon C2 into C2 upon C2 plus Cc is equals to K upon 1 plus K2. C1 upon C2 plus Cc is equals to K upon 1 plus K2 is equals to K3. C2 plus Cc is equals to total concentration of normal molecule and solvated solute molecule in phase 2. Therefore, equation of 4 may be written as total concentration of solute into in phase 1 upon total concentration of solute into in phase 2 is equals to constant. It is evident that when the solute molecules enter into chemical combination with solvent molecule, the distribution law does not get modified. However, there is change in the numerical value of the constant. Thermodynamic derivation of the distribution law. The derivation of distribution law from thermodynamic is based on the condition that in a phase equilibrium between two immiscible liquid containing the same solute dissolved in them, the chemical potential of the solute must be same in both phases. Suppose the solute is present in between immiscible solvent A and B in contact with each other. The chemical potential in solvent A is mu A and in solvent B is mu B. At equilibrium, the chemical potential of solvent in both the phases is equal that is mu A is equals to mu B. From thermodynamics, we know that chemical potential of a substance is given as mu is equals to mu naught plus RT ln A, where mu naught is the standard chemical potential and A is activity of the solute in a solution. Therefore, mu A is equals to mu naught A plus RT ln AA for phase A, first equation, and mu B is equals to mu naught B plus RT ln AB for phase B, second equation. Hence, mu naught A plus RT ln AA is equals to mu naught B plus RT ln AB, third equation. Number RT ln AA upon AB is equals to mu naught B minus mu naught A, fourth equation. ln AA by AB is equals to mu naught B minus mu naught A upon RT, fifth equation. At constant temperature, the standard chemical potential mu naught A and mu naught B for a given solute in a particular solvent are constant. Since R is also constant, it follows from equation 5 that ln AA by AB is equals to constant, AA by AB is equals to constant. Sixth, seventh equation. Since the solution are dilute, therefore the activities are equal to concentrations. So equation 7 becomes Ca by Cb is equals to constant is equals to K. This is the Nernst distribution law. It is applicable in this form when the solute is normally distributed in both the layers. However, it gets modified in the cases when the solute undergoes association, dissociation, or enters into chemical combination with one of the solvents. Application of distribution law. There are many applications of distribution law in laboratory and in industry. Some of these are briefly discussed here. Number 1. In calculating solubility of a solute in a solvent, when a solute is shaken with two immiscible solvents in contact with each other at equilibrium, both the solvents are saturated with the solute. Therefore, the concentration at equilibrium are equal to the solubility of solute in both solvent. We can write the distribution law as C1 by C2 is equals to S1 by S2 is equals to K, where concentration C1 is equals to S1, the solubility of solute in solvent 1, and concentration C2 is equals to S2, the solubility of solute in solvent 2. Hence, knowing the value of the distribution constant K and solubility of solute in one of the solvent, the solubility in other solvent can be calculated. Distribution indicators. Certain solvent can appreciably dissolve even the small amount of solute present in some other solvent. When such a solvent is added to a dilute solution of the solute in some other solvent, most of solute gets distributed into this solvent. Hence, it acts as an indicator for the presence of even a small amount of the solute. For example, a dilute solution of iodine in water is almost colorless. Iodine is considerably soluble in CS2. Its distribution coefficient between CS2 and water is 400. Therefore, an extremely dilute solution of iodine can be estimated by adding a few drops of CS2 to its aqueous solution. A sufficient amount of iodine passes into CS2 layer and gives it a deep violet color. This solution may be titrated against sodium thiosulfate solution till the violet color in CS2 layer disappears. Hence, CS2 can serve as distribution indicator in iodometric titration, in which iodine is produced during titration. In determining the extent of association or dissociation of a solute in a solvent, using distribution law, the molecular state of a solute in a solvent can be determined in the distribution experiment. If the ratio of concentration of solute in both the solvents, that is C1 by C2, is constant, then the solute behaves normally in both the solvents. When a solute X undergoes association in one of the solvent and next to Xn having concentration C2 in it, then the distribution law modified as C1 upon N under root C2 is equals to K. From the value of N, the molecular mass of the solute in this solvent can be calculated by multiplying the actual molecular mass by N. For example, benzoic acid in a mixture of water and benzene exists as dimer in benzene. Hence, the value of N is equals to 2. Therefore, the molecular mass of benzoic acid in benzene is 2 into 122 is equals to 244. The value of N in above expression can be calculated by one of the following method. A. By hit and trial method. The values of C1 and C2 are obtained experimentally, and C1 upon under root N into C2 is equals to K are put in the following equation. Then putting N is equals to 234, the corresponding value of K are calculated. The number which gives the constant value for K is the correct value of N. B. Logarithmic method. We have the equation C1 upon n under root C2 is equals to K. C1 by C2 1 by n is equals to K. C1 is equals to C2 whole power 1 by n into dot K. Taking logs on both sides. Log C1 is equals to 1 by n log C2 plus log K. For two experimental values C1, C2 and C1 dash C2 dash, we can write log C1 is equals to 1 by n log C2 plus log K. Log C1 dash is equals to 1 by n log C2 dash plus log K. On subtracting equation 2 from equation 1, we have log C1 minus log C1 dash is equals to 1 by n log C2 minus log C2 dash. N is equals to log C2 minus log C2 dash upon log C1 minus log C1 dash. Hence, n can be calculated. Similarly, when a solute dissociates in one of the solvent in which its concentration is C2, but then the distribution law is applicable as C1 upon C2 into 1 minus alpha is equals to K. Thus, if the degree of dissociation alpha of the solute is known at the concentration, the value of alpha at any or other concentration can be obtained using above equation since K is constant. In the study of chemical equilibrium involving formation of complex ion, an important application of distribution law is to study the equilibria involving complex ion. Consider some reaction involving formation of complex ion. K1 plus I2, Ki3. I negative plus I2, I negative. I3 negative complex ion. KBr plus Br2, KBr3. Br negative plus Br2, Br3 negative complex ion. CuSO4 plus 4NH3, Cu into NH3 whole 4SO4. Cu2 positive plus 4NH3, CuNH3 4 into 2 positive whole 2 positive complex ion. Using distribution law, the equilibrium constant of any of these reactions can be calculated on the basis of consistency in the value of equilibrium constant. The formula of the complex can be found out. The application of distribution law in determining the formula of complex ion I negative 3 is described as follows. Number 1, a solution of iodine in CH2 is shaken with water to determine the distribution coefficient of iodine between CH2 and water. Number 2, a solution of iodine in CH2 of known concentration C moles per liter is shaken with an aqueous solution of Ki of known concentration say B moles upon liter. Number 3, after the equilibrium is established between two layers, the concentration of iodine left in CH2 layer is determined volumetrically by titrating it against standard hyposodium thiosulfate solution. The equilibrium constant is calculated as follows. Let the initial concentration of iodine in CH2 layer is equals to moles per liter. The initial concentration of Ki solution is equals to B moles per liter. Distribution coefficient of iodine between CH2 and water is equals to K. Concentration of iodine left in CH2 layer is equals to C moles per liter. In aqueous layer, I2 react with Ki, therefore total concentration of iodine in aqueous layer will be much higher due to formation of soluble complex Ki3. Total concentration of I2 free iodine plus combined in aqueous layer is equals to initial concentration of iodine in CH2 minus initial concentration of iodine left free in CH2 layer is equals to A by A minus C moles per liter. Concentration of free iodine in aqueous layer can be calculated according to distribution law. Concentration of free iodine in aqueous layer upon concentration of iodine in CH2 layer is equals to K. But the concentration of iodine in CH2 layer is equals to C moles per liter. Concentration of free iodine in aqueous layer is equals to Kc moles per liter. That is, the concentration of iodine that can combine with Ki is equals to A minus C minus Kc moles per liter is equals to D moles per liter. According to the reaction, Ki plus I2 is equals to Ki3. Number of moles of I2 combined is equals to number of moles of Ki combined is equals to number of moles of Ki3 formed. Concentration of Ki3 in aqueous layer is equals to D moles per liter. Concentration of Ki in aqueous layer is equals to B minus D moles per liter. Concentration of iodine in aqueous layer is equals to Kc moles per liter. Applying law of chemical equilibrium, we can write K dash is equals to Ki3 upon Ki dot I2. Taking different initial concentration of iodine and Ki solution, the value of K dash is calculated for each set. The consistency of value of K dash shows the formula of complex is Ki3 or that of complex ion. Complex ion is I3 negative. in the process of extraction. Another important application of the distribution law is in the process of extraction in laboratory as well as in industry. In laboratory, for instance, it is frequently used for the removal of dissolved organic substance from aqueous solution with solvents such as benzene, ether, chloroform, carbon tetrachloride, etc. The advantage is taken of the fact that the partition coefficient of most of the organic compound is largely in favor of organic solvent. In industry, the process of extraction is used to remove the impurities from the product. The aqueous solution of the substance to be extracted is shaken with an organic solvent in which it is highly soluble. After shaking vigorously, the mixture is allowed to stand for some time. The two layers are then separated using a separating funnel. The organic solvent is cornered by distillation and used again for the extraction process to be more effective, efficient. Following conditions should be fulfilled. Number 1, the distribution coefficient of the substance between the extracting solvent and the solvent in which it is already dissolved should be very high in the favor of extracting solvent. Sometimes the distribution coefficient in the extracting solvent is artificially increased by making the substance less soluble in the aqueous phase. This can be done by adding some substance with decrease the degree of dissociation of the compound in aqueous phase. For example, acetic acid with which weakly ionizes in aqueous solution is to be extracted with ether. A strong acid, say HCl, is added to the solution. Due to ionization of HCl, the H positive ion concentration increases, and due to common ion effect, the ionization of CH3COH is suppressed. As a result, there is greater concentration of unionized acetic acid. Hence, greater amount of acid will be extracted in ether layer. Similarly, the extraction of organic base from its aqueous solution into organic solvent can be increased by adding strong inorganic base. In general, the solubility of an organic compound in water can be decreased by adding salts. Hence, its distribute coefficient increase in favor of extracting solvent. This is termed as a salting out effect. Thus, we conclude that greater the distribution coefficient in the favor of organic solvent, greater will be the amount extracted. Number 2, to recover the maximum amount of substance, the extracting solvent should be used in one lot, rather it should be used in maximum number of installment. This is called multiple extraction or multi-step extraction. The fact that it is more efficient to use extracting solvent in small portion rather than in one lot is illustrated as follows. Suppose Ag is of the substance is present in 1 liter of aqueous solution. We can extract the substance with ether as the distribution coefficient of the substance between ether and water is number 2. We are provided with 1 liter of ether which may be used in 1 lot or 2 installment of 500 cc each. Number 1. Using all ether in 1 installment. Let X of substance be extracted in the extracting solvent, then the amount of substance left in aqueous layer is equal to A minus X gram. Therefore, concentration in ether X upon 1000, concentration in water A minus X upon 1000. According to distribution law, C ether upon C water is equal to K. X upon 1000 upon A minus X upon 1000 is equal to 2. X is equal to 2 by 3, A is equal to 0.67 A. Thus, only 67% of total amount will be extracted. Extraction using 500 ml of ether. Let X1 grams of substance be extracted in the first installment of 500 ml ether. Thus, concentration in ether is equal to X1 by 500. Concentration in water is equal to A minus X1 by 100,000. C ether upon C water is equal to 2. Therefore, X1 by 500 upon A minus X1 by 1000 is equal to 2. That is, X is equal to 1 by 2A. Therefore, 50% of substance will be extracted in one installment. That is, the substance left in aqueous layer is equal to A minus 1 by 2, A is equal to 1 by 2A. Now, 1 liter of aqueous solution containing 1 by 2 Ag of substance is extracted with 500 ml of ether. Let X2 gram of the substance be removed from aqueous layer to 500 ml ether. Thus, the concentration in ether is equal to X2 by 500, concentration in water 1 by 2A minus X2. C ether upon C water is equal to 2. X2 by 500 upon 1 by 2A minus X2 upon 1000 is equal to 2. X2 is equal to 1 by 4A. Hence, 25% of the substance is extracted into ether layer. Total amount of substance extracted is equals to 50 plus 25 is equals to 75%. Thus, when the substance is extracted using 500 ml portion of the solvent, the percentage extraction increases from 66.66 to 75. Similarly, it can be shown that using the same 1 liter of the solvent in 4 installment of 250 ml each, 93.75% of the substance can be extracted. Thus, it can be concluded to do more efficient extraction, it is better to use a given quantity of solvent in small portion. However, it must be noted that it is not possible to extract whole of the dissolved substance. However, large number of extraction may be carried out. Every time the substance distributes itself between two solvent and some amount is always left unextracted. General formula for the substance left extracted. General expression to calculate the amount of substance left extracted unextracted after a given number of operation is derived as follows. Suppose W gram of the substance is present in V ml of the solution made by using solvent A. It is extracted with extracting solvent B using V ml of B each time. K is the partition coefficient of the substance between solvent A and B. Let W1 gram with the amount of substance left unextracted in solvent A after first extraction. The distribution coefficient at the first stage is given as concentration of substances original solvent A upon concentration of substances extracted in solvent B is equals to K. W1 upon V upon W minus W1 upon V is equals to K. W1 upon V is equals to KVW minus KVW1. W1 is equals to KV plus V is equals to KVW. W1 is equals to KV upon KV plus V into W. Now, after the second extraction, if W2 gram is the amount left unextracted in solvent A, then the amount of substance extracted in W1 minus WG gram. W2 into G. For the distribution law, W2 upon V upon W1 minus W2 upon V is equals to K. W2 is equals to W1 dot KV upon KV plus V. Substituting value of W1 from equation 1, we get W2 is equals to W into KV upon KV plus V is into KV upon KV plus V. Up is equals to W into KV by KV plus KV in whole power square. In general, the amount of substance that remain unextracted after nth extraction will be Wn is equals to W into Kv by Kv plus V whole power n. To make extraction process most efficient, Wn should be the smallest possible. This can happen in term is made as small as possible. In this term, the denominator Kv plus V is bigger than numerator Kv. Hence, the factor Kv upon Kv plus V is less than into 1. Therefore, factor Kv by Kv plus V whole power n will be least for the greater value of n. Greater value of n, the efficiency of extraction increases by increasing the number of extraction using only a small amount of extracting solvent each time. This is obvious that the better efficiency can be achieved by keeping V small and n large. So it follows the multiple step extraction is more economical than the single step extraction. Also, it is clear from equation 4 that Wn can never be equal to 0. However, large value of extraction may be carried out every time the remaining substance distributes itself between the two solvents according to the distribution law. The principle of multi-step extraction is applicable to washing of precipitate. If the repeated washing of precipitate with small quantity of solvent, the impurities are extracted to a large extent. The principle of extraction is used in Park's process for desilverization of lead. Silver is more soluble in zinc than in lead. The argentiferous lead is melted and heated to 880 degrees Celsius and then molten zinc is added. Molten zinc is immiscible with molten lead, hence form two immiscible liquid in contact with each other, and silver behaves as a solute which is more soluble in zinc than in lead. The partition coefficient of silver in favor of zinc is 300 at 880 degrees Celsius. Silver therefore passes readily from the heavier lead layer into the lighter zinc layer, which is then separated by repeating the process 3 to 4 times. Almost the entire amount of silver passes into the zinc layer, hence almost whole of the silver can be extracted from organoleptous lead. In the number 6, in the determination of the degree of hydrolysis. Hydrolysis is defined as the process in which water reacts with salt to form an acid and a base. Some terms related to salt hydrolysis. Number 1, hydrolysis constant. A general hydrolysis reaction of a salt Pa with respect written as Pa plus H2O into Ha plus BOH. Applying law of chemical equilibrium, the equilibrium constant can be written K is equals to Ha dot BOH upon Ba dot H2. Since the concentration of water is very large, it is regarded as a particularly constant. This expression 1 may be written as Ha into BOH upon Ba is equals to K into HO is equal to O is equals to KH, where KH is the hydrolysis constant. In expression 2, Ha and BOH are the molar concentration of acid and basis product, and Ha is the molar concentration of unhydrolyzed salt. The above expression can be written as KH is equals to free acid, free base, and unhydrolyzed salt. Degree of hydrolysis. The degree of hydrolysis of a salt may be defined as the fraction of the total amount of salt which is hydrolyzed at the point of equilibrium. For example, in aqueous solution of aniline hydrochloride, 80% of the it hydrolyzed into aniline and hydrochloric acid. Then the degree of hydrolysis is 0.80 degree percent. The degree of hydrolysis is represented H. Mathematically, H is written as H is equals number of moles of salt hydrolyzed upon total number of moles of salt. Expression for degree of hydrolysis of different type of salt. The salt of strong acid and strong base such as NaCl, Na2SO4, etc. do not undergo hydrolysis. Therefore, for such salt, expression for KH and H are not written. These constant for the other three type are: number 1, salt of weak acid or strong base. Hydrolysis reaction of salt Ba is written as Ba plus H2O is BOH plus He. In aqueous solution, Ba and strong base BOH undergo complete dissociation, whereas Ha, being weak acid, remain unassociated. Thus, the salt of weak acid and strong base undergo anionic hydrolysis. In the initial concentration of salt is C moles per liter, and H is its degree of hydrolysis. Initial concentration C. A negative plus H2O into OH plus H. Initial concentration C 0. Concentration at equilibrium C into 1 minus H CH. Hydrolysis constant KH is equals to OH negative onto Ha upon A negative is equals to CH square upon 1 minus H. If small h is the quite small as compared to 1, then 1 minus h is nearly equal to 1. Expression become KH is equals to CH square. H is nearly equal to KH upon C under root. H is directly proportional to 1 upon under root C. Thus, the degree of dihydrolysis of a salt of a weak acid and strong base is inversely proportional to square root of its molar concentration. Salt of a strong acid and strong weak base. General hydrolysis reaction of Ba plus H2O is BOH plus He. Salt of Ba and strong acid H are completely dissociated. Hence, this salt undergo anionic hydrolysis. In this case, hydrolysis constant is given KH is equals to BOH into H positive upon B positive is equals to CH square upon 1 minus H is equals to KH. H is less than 1, therefore above equation becomes CH square is equals to KH. H is equals nearly equals to 1 root KH upon C. Salt of weak acid, weak base. The salt of weak acid and weak base Ba undergo hydrolysis. Ba plus H2 is equals to weak base plus weak acid. Weak acid and weak base are weakly dissociated, but salt of Ba is completely dissociated. It involves both cationic hydrolysis as well as anionic hydrolysis at equilibrium. Initial concentration Cc 0. Concentration at equilibrium 1 minus Hc into 1 minus H CH. KH is equals to CH dot CH upon C into 1 minus H dot C into 1 minus H is equals to H square upon 1 minus H square. Therefore, above expression can be written as KH is equals to nearly equals to H square, because 1 minus H nearly equals to 1. H is nearly equals to 1 root KH. It is important to note the expression does not involve concentration term C. Application of distribution law is in determining the degree of hydrolysis. Aniline hydrochloride is salt of weak base and a strong acid HCl. Its degree of hydrolysis is determined as: Step 1. Determination of hydrolysis constant. Aniline hydrochloride is hydrolyzed according to the reaction. Hydrolysis constant is given as C6H5NH2 plus NH2 free aniline. KH is equals to C6H5NH2 dot HCl upon C6H5NH3Cl. To calculate the above concentration in aqueous solution of aniline hydrochloride of known concentration is taken with the known volume of benzene. On standing the mixture of separate into two layers, free aniline get distributed between water and benzene, while HCl and unhydrolyzed salt remain in the aqueous layer. Number 1. Determining the concentration of free aniline in the aqueous layer. A known volume of benzene layer is taken out. The solvent is evaporated, then the bed of aniline left behind is found. From this, the concentration of aniline in benzene layer is calculated. The concentration of aniline in aqueous layer can be calculated using distribution law. Number 2. Determination of concentration of free HCl in aqueous layer. Free hydrochloric reaction, it is clear that number of moles of HCl set free is equal to the total number of moles of aniline produced. For the total number of amount of aniline produced is equal to amount of aniline present in aqueous layer of aniline of plus amount of aniline in benzene layer. The concentration of free aniline in aqueous layer and benzene layer is calculated in step 1 above. From these values, the number of moles of free HCl produced is also calculated. From the volume of aqueous layer and number of moles of HCl, the concentration of free HCl in aqueous layer can be calculated. Number 3. Determination of concentration of unhydrolyzed salt in aqueous layer. Again, from hydrolysis equation, it is seen that number of moles of aniline hydrochloride hydrolyzed is equal to total number of moles of free aniline or HCl produced. The quantity of RHS has been calculated in step 3 above. Therefore, the total number of moles of aniline hydrochloride hydrolyzed is obtained when this is subtracted from the initial number of moles of the salt. The number of moles of unhydrolyzed salt can be calculated from the volume of aqueous layer. The concentration of unhydrolyzed salt can be calculated substituting the value of calculated in step 1 to 3. In equation 1, the hydrolysis constant KH of the salt can be calculated. Number 4. Calculation of degree of hydrolysis of aniline hydrochloride. After calculating the hydrolysis constant KH as discussed above, for a solution of the salt having concentration C moles per liter, the degree of hydrolysis can be calculated using expression H is nearly equals to KH upon under root C, under root KH upon C. Thank you.